In this video, I'll be going through the final part of the ISP on Unit 5 of Oscillation, Thermal and Nuclear Physics. And this one is all about the idea of nuclear physics or radiation. So the task involves the description of 3 types of radiation, an explanation of what radioactive decay actually is, a definition of the term binding energy, and the process of nuclear fission and fusion. Try to make links back to E equals mc squared and atomic structure, which we did in Unit 4. So, explaining everything task, the first one, define the term half-life and describe more than one method of finding it. So remember, the half-life is the time it takes, remember half-life is a measure of time, okay? The time it takes for the number of radioactive isotopes remaining, of radioisotopes to half, okay? Or half the number of radioactive isotopes to decay. So the time it takes for the number of radioisotopes to half, or half the radioisotopes to decay, whichever way around you want to say that is fine. Or it could be the count rate instead of the number of radioactive isotopes. Methods of finding it, what is the equations? Okay, so there's n is equal to n naught e to the minus lambda t, okay, where lambda is a decay constant, sorry, the half-life, the time, so the half-life will be the time over here, so that is going to be when n over n naught, let's just write it all out and then I'll explain. N naught is your original value, or n is your current value. So when that value is equal to a half, your value of t, you can figure out using an expression. Well, we can go a bit further than that if we want to. What we could actually do is to take a log of both sides, a natural log of both sides. And if we want to get rid of this minus, remember that just inverts. If you get rid of this minus, it just inverts this. The natural log's got rid of the e. If you want to get rid of the minus, it will invert this. So log 2 is equal to lambda t. Therefore, t is equal to log 2 over lambda. So that's one way of finding the half-life. But t is a very specific t. That's t half. That's just log 2. So I should have really replaced all those with halves throughout. Right, another method, if you had a graph of n against t, you could just see the time it took to half. It's pretty straightforward from that. Okay, so if that was 100, and that was 50, just see what that time is. Don't do it once, do it 3 times, see what 25 is, see what 12.5 is, and get averages of those values. Okay, describe an experiment that could be used to find the half-life of a sample. Okay, so that's pretty much exactly what we've just described there. You're using a Geiger-Müller counter to allow you to do this, to measure the count rate. But the key thing is you've got to take a background radiation reading off everything you do. So a background radiation reading has to be taken off every value. So you always take the background radiation reading first. Okay, let's get straight into these questions then. Just gone past it. Right, name 2 sources of background radiation. So you've got the ideas of hospitals, you've got rocks in the ground, you've got cosmic rays, you've got food, you've got nuclear power industry, you've got the atmosphere, you've got medical uses, nuclear weapons testing, the sun, radon gas, any of those are fine. Right. Students doing an experiment with radioactive material. She used a counter to record the total count. Her teacher points out that she has forgotten to measure background count. Describe the procedure this student should follow. You must mention any additional equipment you might need. Okay. So you use a GM tube or a stopwatch and a rate meter. And if you're taking a background count, you've got to make sure everything is, all the sources you're going to use are in their lead containers and they're away from the experiment. You measure the count over a period of time. You don't measure it instantly, you measure it over a period of time, and you divide by the amount of time it actually takes. You repeat it, an average, and you want at least about 5 minutes worth of readings altogether. You take that background count then away from every single reading. So why might it have been unnecessary to actually do this? Well, remember the count rate is going to be ridiculously large, well, normally ridiculously large compared to the background rate. Okay, so background count is going to be background radiation is going to be very, very small. The count rate is usually very, very large, so the comparison, well, there isn't one really, so it's going to make a negligible difference. Recently, some old human skulls have been found in Mexico. Their age has been established using radiocarbon dating. When a nucleus decays, it emits a beta particle. State how the composition of a nucleus changes as a result of the decay. Well, it has one less neutron and has one more proton. So a neutron changes to a proton and releases an electron. That's the idea. When estimating a small sample of these skulls, scientists found that 2.3 times 10 to the minus 11% was carbon-14, whereas in recent skulls it's 1 times 10 to the minus 10. Calculate the age of this skull. So we've got the half-life, we need to calculate the age of it. So, if you want to figure out the age, you've got to essentially use this equation here that we had before to figure out your t. Now we need lambda, but we've got half-life. But we know that we can rearrange this expression here to figure out lambda from half-life. Okay, so let's work through this step by step. T half is equal to ln over 2, ln 2 over lambda, so natural log 2 over lambda. So lambda is therefore equal to natural log of 2 over the half-life. That gives us our half-life value. Then we've got n is equal to n naught e to the minus lambda t. Well, our lambda is now going to be the value from over there, and our t is what we want. Well, let's rearrange this for t to make it easy to begin with. So t, we need to get by itself. So let's bring the n naught over and natural log it. And if we natural log this side, remember the e disappears, left with minus lambda t. Minus disappears if you flip these over, so you're left with n naught over n is equal to lambda t. So t is therefore equal to n naught over n, natural log, sorry. There we go, that's a bit better. And all of that is going to be over lambda, with lambda being equal to natural log of 2 divided by the half-life value that we're looking for. That's pretty straightforward. So there's a lot of calculation to do there, but it's straightforward to the question. You can figure out the values separately if you wanted to, but I find this method easier in terms of rearranging and then submitting my value afterwards, just so I can see all my rearranging. So the time we should get should be about 1.2 times 10 to the 4. The value, give one reason why the value of calculated above may be inaccurate. Well, it's impossible to know the exact amount or the exact proportion or percentage of carbon-14 in the atmosphere when the bones were formed. Okay, so we don't know how much carbon-14 there was in the atmosphere when it was formed. It might be different to what it is now. Recent bones are dated using the decay of lead. Okay, and the reason why is because the half-life is 21 years. It's explained why it's more suitable for recent bones. Well, remember you're going to want a substantial change. Okay, so the half-life is close to the age. You want a half-life that's relatively close to the age of whatever you're trying to actually measure, because you want a numerous amount of half-lives to have passed. So lead is close to the age of recent bones, therefore a greater proportion of lead will have actually decayed as time passed. So in other words, more than one half-life of lead would have passed, while if we tried to use carbon, not even one half-life would have passed for recent things. Okay, for recent objects. Question 8. So define and term binding energy. Common question is the energy required to separate a nucleus into the nucleons that make it up. Okay. Iron has the highest binding energy. What does it tell you about the iron nucleus? Well, it tells you it's the most stable because it needs the most energy to break it apart into its nucleons. Therefore, it must be the most stable. Carbon-14 is unstable and decays by beta emission to nitrogen. Write a full nuclear equation for this decay. Okay, so it's pretty straightforward. Carbon ends up becoming nitrogen and also a beta particle. Okay, so that's going to be 14 and 6. And they've already given you those numbers. Beta particles you need to remember as 0 and -1. So that makes carbon 14 and 7. Remember these numbers need to add up. Remember this is a... Let me get that in there. Remember this is a minus, that makes it trickier. So these numbers across the top need to add up, and these numbers across the bottom need to add up too. Right. So I was just testing to see whether the light would make it any brighter, but it's not. Question 9. So, we've got a grid here. It's got a number of neutrons on one side, a number of protons on the other. Uranium, so you've got protactinium, decays to uranium by emitting a beta minus particle. The uranium produced itself is radioactive, decays by alpha to thorium. Okay, so we're going to go through this step by step. What I'd say the first thing to do actually would be is to write out this entire decay series. So there's your uranium. That becomes... So there's your protactinium, that should be. Oh no, sorry, protactinium becomes uranium. Apologies. Let's write this out here. So uranium's in the middle here. 2, 3, 8. That's going to... also give out a beta particle as it decays. So we can figure out the protactinium that we had beforehand by working through our values. So that's 2, 3, 8, and that's going to be 1 less. And then my uranium is 92, it's going to be 91. Okay, so those numbers now add up. And that's going to become thorium by alpha. So now I need to put the alpha numbers in of 4 of 2. I can't see this, so let me zoom out slightly. Here we go, I need to put the alpha numbers in of 4 and 2. So across the top, that's a 0, that's right. 2, 3, 4, minus 4, that's going to be 230. Minus 2, that's going to be 290. So after that, it's just about plotting the values onto the graph. But remember, it's the number of neutrons, so you need to take one value away from the other to figure out how many neutrons each of these has. Okay. So that one has 143 neutrons. There's 142 neutrons. I don't know why to get to calculate that one. That has 140 neutrons. Okay, so now you know how many neutrons they have, you can plot the points. So these are the points you're plotting for each of these. And you draw the lines that show how they move from one to the next. Remember to label the correct ones alpha and beta. So this one will have the alpha with it, this one will have the beta with it. But they're your 3 points that you plot. So these are your 3 points, and as you go from each to each, you draw on the line beta, or you draw a line on the line alpha. So 14391 would be over here. And that goes to 14292. That's over here, and you label that line beta. And then that goes to 90, 140, 140, 90. So it's over here, and you label that line alpha. Pretty straightforward. Last question to get for 4 marks. It's thought that some soil might be contaminated with a radioisotope. You have a sample of the soil, design an experiment to find out what type of radiation is emitted. So this is an absorber experiment. But remember, the first thing you always need to do in these sort of experiments is to measure background. Okay, so it's a 5 mark question usually, these sort of things. Yeah, there we go. 5 marks. So, you've got to put the soil in a container. Okay, put that container far away, measure the background count. Then you take the soil, put it in a detector, put paper in there first. Remember, paper absorbs alpha. If you don't want to use paper, 5 centimeters of air will absorb alpha as well. So you can put it 5 centimeters away, see what happens, see if you get any reading. If the count rate is reduced, alpha is present. If you put the paper in, it reduces, alpha is present. Or if you move it after 5 centimeters away, and it's reduced, alpha is present. If that doesn't happen, and you put an aluminium foil, then beta is present. Only if the count rate reduces. So if the count rate reduces when you move it away, it's alpha. Don't go any further. You figured out it's alpha. If you then put in aluminium, if it doesn't reduce and you put an aluminium foil, it's beta. If it doesn't reduce, but you put a lead sheet in, and then it does reduce, then it's gamma that's present. If there's no count after aluminium, and none after gamma, well, if there's no count after aluminium, essentially, and there's no count after lead, then it must have been alpha. If the movement made a difference. Right. So that covers the 5 main sort of points that that you could have gained from that question. So I'll show you the mark scheme for that, so you can see clearly how I sort of phrased my thinking. But just remember, it's about going through alpha, beta, and gamma in order. So you can see that over here, and that brings us to the end of our ISP on nuclear physics. Thank you for watching.